To the another lecture of the series of control of power electronic converters. So in this lecture we'll discuss about controller design in frequency domain. So in the last lectures we have seen how to design a controller in time domain, considering the time domain specification, like for a given rise time, then for a given settling time, then for a given overshoot, and based on the limitations, how to tune the KI KP parameters for a first order and second order systems. So we have seen that by if we just keep on substituting some inequalities, by solving them we can get the desired converter response by ensuring that the closed loop response is stable. It is getting the desired steady state error, and it gives the desired transient responses. Transient responses means rise time, settling time, and overshoot. And we also know that as we go on increasing the order of the system or the order of the plant, the identities become complex to visualize. Like here in this case, for a second order system with a PI controller, it became overall a 3D graph, basically a 3D complex plane. It became a 3D complex plane. So in this case, the controller design becomes slightly challenging. So that's why people prefer controller design in frequency domain, where you have to you can design the KI KP parameters by just assuming a given phase margin and bandwidth out of the crossover frequency. So we'll start with today's lecture, and we'll see about the frequency domain analysis. So basically the methodology to tune the parameters, the controller parameters using the OLTF controller design. It is typically based on, there are different methods like root locus, then we have frequency domain analysis, which is also called as loop shaping analysis or Bode plots. These are the two methods typically used for designing the controller. So I think we already have seen in bachelor's course that how to use the root locus technique. So basically in root locus technique we use the closed loop controller, the overall transfer function for a closed loop system, and then we match it with the characteristic equation, and then we keep the coefficient of all the powers of S to be of the same sign, and then we do some plots, and then we find the KI KP values. So but frequency domain analysis is mostly preferred by power electronic engineers, so we'll be using the frequency domain analysis. So specification of frequency domain analysis are first one is the margins, gain and phase margin. So gain margin is denoted by GM, either in GM in decibel or GM in absolute scale, and phase margin is PM in degrees or phase margin in radians. So these are basically the margins. Second thing is the crossover frequencies. First is called as the gain crossover, means omega GC in radians per second, and the next one is the phase crossover, is omega PC in radians per second. So these are the the last one is the closed loop bandwidth, or omega BW of CL, closed loop bandwidth. So we'll just quickly see what is the definition of these parameters. So let's say G of S is the plant transfer function. So first one is the gain margin. So gain, okay, first we'll see, instead of instead of margins, we'll first see the crossover frequencies. Omega gc. Omega gc is omega at which gain crossover at which the mod of g of j omega equals to 1 or 20 log base 10 of mod of g of omega equals to 0. This is in absolute and this is in decibel scale, 20 log base 10 of this semi-log scale. So because in body plots we use the semi-log scale for the gain plot instead of the absolute unit. So gain crossover frequency is the frequency at which the gain is crosses, means the gain plot crosses the 0 dB line or the 1 for absolute scale. Then comes the phase crossover frequency. Phase crossover is the frequency at which angle of g of j omega gc is equals to minus 180 degree or minus pi radian. So this is the angle at which the phase plot crosses the minus 180 degree line or minus pi in radians. Then comes the margins. First is I'll write the phase margin. So the phase margin is the basically the definition is the maximum phase that can be added to a plant okay, instead of plant I'll write g of j omega, so that the GCL of S or G equivalent of S or the closed loop transfer function is stable. Similarly, I'll just copy paste. So gain margin is the maximum gain that can be added to a plant so that its closed loop response becomes stable. So what is the thing that adds the gain or adds to the phase to a plant that can be added? I'll write by a controller d of omega. Okay, that can be added by d of omega. And you know the open loop transfer function OLTF is d of s into g of s. So I'll just pictorially represent what are the gain margin and phase margins. So let's say g of s is k by, or let's say instead of k by s I'll write 1 by 1 plus s into tau, where tau is a so basically it's a low pass filter and tau is the time constant of the low pass filter. So tau is a constant. So if we just write it in g of j omega, if you substitute g of j omega and separate out the real and imaginary part, it will be g of j omega into tau. So if you just to multiply it by 1 minus j omega tau on both the sides, it will be 1 minus j omega tau. A plus b into a square minus, it becomes plus omega square tau square. So it will be 1 by 1 plus omega square tau square minus omega tau into j by 1 plus omega square tau square. So what is the gain? It is nothing but under root of a square plus b square. So under root of 1 plus omega square tau square divided by 1 plus omega square tau square whole square. So it becomes this 1 plus omega square square. Yeah, this is the gain plot. This is the gain value. So log 20 log base 10 of mod of g of j omega becomes 20 log base 10 of this. So the denominator has the power of okay, let me write 1 plus omega square tau square to the power of minus half. So what happens now, it's a power function. Let's remove the power and it will be like this. So it will be 20 into log of a to the power n is n log a. So it will be 20 into minus half into log base 10 of this 1 plus omega square tau square. It will be minus 10 log base 10 of 1 plus omega square into tau square. So this is the log scale. This is the log value. Now, but okay, then let me write the phase value. What is angle of g of j omega? That is tan inverse of b by a. So that is with tan inverse of b, that is minus omega into tau, or minus tan inverse omega tau. Okay, now in order to draw the frequency response plot of this first order plant or the low pass filter, this is 20 log base 10 of mod of g of j omega. Let me just shift it down. Yeah, and this is versus omega, and then this is the on the same graph we have, means I'll draw this becomes omega, and this is angle of g of j omega. Okay, so we have to draw this. Now what happens is that till this frequency, which is the cutoff frequency of omega equals to 1 by tau, till omega equals to 1 by tau, the gain will be almost constant, and after that it will start to fall with a slope of minus 20 decibel per decade, because it is a pole. 1 plus s tau is in pole, so the gain will be constant till this frequency. What is the frequency? Omega, let's call it as a cutoff frequency, that is 1 by tau. After this it will start falling, so this slope is minus 20 decibel per decade, because it's a y versus x graph and the y axis is in decibel scale. So this frequency, so I told you the frequency at which the gain plot in decibel cuts to 0 is called as the gain crossover frequency. Okay, now let's quickly draw the phase plot of this. So it's basically a first order plant. So what happens, so just substitute omega equals to, initially say this is omega equals to 0, then 1 by tau c omega gc and some value. So here what happens is, instead of omega, the Bode plot is in log of omega, log base 10 of omega for the gain plot, in order to show the decades. So this will be 10 to the power 1, 10 to the power 0, 10 to the power 2, and this like 10 to the power 5 or 6, like this it will go on. That's why in semi-log versus log scale, it is y equals to mx plus c, this gain plot, 20 log base 10 of mod of g of j omega. So this is a semi-log versus log scale, so it is y equals to mx plus c. And Yeah. So if we no if we don't remove the power of it, so what will happen is this thing, this 20 is here. So 20 log base 10 of this is 20 into log base 10 of this. So what is the decibel and what is the decade? So what is the gain? That is 20, y equals to mx. So this is the slope, 20 minus 20 decibel per decade. So that's why it's a straight line, because it's a semi-log versus log scale. That's why it's almost a straight line. And even if it is not a log scale, we almost assume it to be a straight line. We can assume the gain plot to be a straight line, almost a straight line, but for phase plot we cannot assume it because it's a tan inverse function. Okay. So what happens if for 10 to the power 0, what is the angle? Tan inverse of tan inverse of 0 is what? 0. So this is the 0 phase, 0 degree. It starts with 0. And what happens? Tan inverse function is what? This is basically a tan inverse function is of this nature. So now we are tan inverse of omega. We are not taking this region, we are taking only this right hand side region. So it should rise in a quadratic term or a cubic term like this. So basically it's a cubic term, because we are not taking this side, we are taking this side. This is tan inverse of theta, and this is theta, this is tan inverse of theta. But here the phase falls from 0, it becomes negative because it is minus of tan inverse. So basically multiply a negative sign, so minus tan inverse of theta is this, like this. It will be somewhat like this. So that's why from 0 it is falling like this. But at omega crossover frequency, what means at omega gc as 1 by tau, so let's put it as omega as 1 by tau, so it will be minus tan inverse of 1. That is what angle? 45 degree. Okay, correct. Tan inverse of 1 means y equals to tan inverse of 1, so tan y is 1. So what is the theta? It is 45 degree. So it is like this. It falls. Okay. It falls like this. So this is minus 45 degree. Minus 45 degree, and it goes down. And then what happens? As the omega becomes infinity, it becomes parallel to this axis. Similarly, it should become parallel to this axis, omega axis. So it will be like this. Okay, I think it's not drawn properly. Let me redraw it again. So it becomes parallel to this. So at infinity, what is the angle that we have to see? Minus 45 degree. So what is infinity? When tan becomes infinity, when the denominator becomes 0. So when this cos becomes 0 at 90 degree. So it is minus 90 degree. This point is minus 90 degree, this is minus 45 degree, and this is 0 degree. So this is the phase plot. This is the phase plot and this is the gain plot. So this is the gain crossover frequency, and phase crossover frequency means where it cuts minus 180 degree. Okay. Here. So this becomes minus 180 degree. So draw a parallel line to this. So this is a special case where this graph does not touch minus 180 degree. So it touches infinity. So in this case, omega pc is infinite because it is almost parallel to it. The phase plot does not cut minus 180 degree line. Phase or crossover frequency is infinite. Gain crossover frequency is 1 by tau. Okay, 1 by tau. Then what is this? So now let's measure what is the phase margin. So at gain crossover frequency, at this omega gc, extend this line in this direction and see how much it is above minus 180 degree. So basically this is the phase margin. So if phase crossover frequency is infinite, what is the gain margin? Gain margin is how much is the gain when it is infinite. So basically what happens is it will be infinite. It will also be infinite because we don't know what is the frequency at which it touches minus 180 degree. Let's say it touches infinity. At infinity, how much the gain will be above it, that we don't know. So we have no idea about it. And at gain cross frequency, what is the phase margin? So phase margin is this minus this. So I'll draw an arrow like this. This is the phase margin. The significance of the arrow is this value minus this value. So minus 45 degree minus of minus 180 degree. So 180 minus 45. What will be 135 degree. Positive. Phase margin is positive. Gain margin is infinite. So this is the example of gain margin and phase margin. Also, let's see another. Let's see a generic example. Generic example where let me draw. This is the. Let me write mod of g of j omega in decibel. Means it is understood that it is in decibel, and this is log of omega. So let's see. It cuts and it somewhere it falls like this straightly, and then again it becomes a flat. Similarly, this is the angle of g of j omega gc, and this is the omega. So it is like this. This is the gain crossover frequency, and say this is 0 degree minus 90 degree minus 180 degree. So say that it starts from minus 180 degree, cuts 180 degree, and then at 270 degree it becomes a constant. Say this is a example, just an example. Minus 270 degree is this thing. Means it becomes flat at this point. So at minus 180 degree, see where the point cuts it. Extend it upwards for the gain margin. So this is the frequency at which the gain plot cuts the minus 180 degree line. So this point will be phase crossover frequency. So gain crossover frequency, extend this graph down and see where it cuts the phase plot, and see how much it is above the 180 degree. So this will be phase margin in degrees, and similarly this will be gain margin in decibel. So this is the classic generic example of it. So just let me quickly write. Omega gc is where 20 log base 10 of mod of g of j omega, where omega is omega gc, it becomes 0. At phase crossover frequency, angle of g of j omega pc becomes minus 180 degree. Or you can write in like this, omega, where omega equals to omega pc, like this you can do. Then gain crossover, so phase margin. Phase margin is what? This point minus this point. What is the first point? Arrow indicates subtract this from this. So means what is this point? This point is angle of g of j omega. But what is omega? What is the frequency? Extend the line up. It is omega gc. So angle of g of j omega gc minus of minus 180 degree. So it will become plus 180 degree. So this is the phase margin. Then gain margin. What is gain margin? Again, this arrow, this point minus this point. What is this point in decibel? It is 0 decibel. And what is this point in decibel? this point is 20 log base 10 of this and this, so it becomes 0 minus 20 log base 10 of mod of g of j omega. Now what is omega? Gain margin is at phase crossover frequency, so omega pc. Ultimately it becomes gm equals to, this is the phase margin, minus 20 log base 10 of mod of g of j omega pc, or gm equals to what? 1 minus this, because in absolute what is the, this point, this is 1 in absolute and 0 in decibels, so 1 minus mod of g of j omega pc. This is in decibel, this is in absolute. So these are the definitions of gain and phase margins. So these are the definition of gain and phase margins. So gain and phase margins, whenever I say the word margins on crossover frequencies, so as of now I'm considered only a plant. So I know the model of a plant. I have considered a first order plant. I have put s equals to j omega, taken the real and imaginary parts, plotted the gain plot as semi-log versus log axis, and it came out to be a straight line after this cutoff frequency. So basically omega c is called as the corner frequency, or omega c, I forgot one thing, is called as the corner frequency. Corner frequency means the frequency at which the slope of the plot changes. So basically if the gain plot is 1 by s into s plus a into s plus b, so at two frequencies, as there are three gains, so at two frequencies the gain should change. So there are two corner frequencies. Here there is only one corner frequency. Initially the slope was 0, then it become minus 20 after omega c point. Then I have drawn the gain plot, the phase plot, and then define the crossover frequencies, and then define the margins. So as of now it's for a plant. So whenever I say the word margin, gain or phase margin, it's for a plant, not for the closed loop system or not for the open loop system. Okay, so gain margin is this much is the margin, means this much gain you can add in decibel. And what is the thing that adds the gain? A controller adds the gain. So d of j omega should add that gain at omega pc. Similarly, phase margin is the angle of d of j omega. What should that be? That is maximum of this. So I can write this right 20 log base 10 of mod of d of j omega, first at the gain margin, so at phase crossover frequency. This should be less than or equals to gain margin in decibel. What I said, gain margin is the maximum gain which can be added by the controller. Maximum means less than equals to at the phase crossover frequency. And okay, or I'll write mod of d of j omega pc should be less than equals to gain margin in absolute, like this much gain I have to add. Similarly, angle of d of j omega phase crossover frequency at gain means phase margin at gain crossover frequency. So angle of d of j omega gc should be less than or equals to phase margin in degrees. This is in degrees, so this is in degrees. So this is what is the requirement of a controller, because margin means till the value which you can add gain and phase at some known frequencies. So omega gc, omega pc are known frequencies. Now one more thing, like should we consider gain margin or phase margin or both while designing the controller? Now in this classical example of a first order plant, here the phase crossover frequency is infinite, so gain margin is undefined. Instead of writing undefined, I'll write infinite, I'll write undefined. Okay, undefined. So basically phase margin is sufficient to design the controller. There should not be a strict restriction on of the gain margin and all, that you should also work on gain margin. Phase margin is sufficient because of this term, because of this case, special case. So why? Because the phase plot may or may not be up to 180 degree. Now what is the thing that rolls or the shifts the graph from vertically in this thing? Let's say this is the graph, this is the phase graph. What is the thing that will shift this graph up and down? It is nothing but the integrator action. Means if whenever the plant has an integrator, so let g of j omega equals to, say, some let's say it is like this, s to the power m into s plus a into s plus b into s plus c, like this. So what happens? There are some frequencies j omega a by b or b by a. This is j omega plus a. Okay, so it is omega equals to 1 by a. Omega equals to 1 by a. There are three corner frequencies. Omega equals to 1 by b and omega equals to 1 by c. Three corner frequencies. 1, 2, 3. 1 by a, 1 by b, 1 by c. So it means there are 4 regions. There are 4 terms here on the pole side. Let's say the 0 side is a constant. Or okay, let's have something on this side also. So s plus a1, s to the power n, s plus b1 into s plus c1. Then we have a1, 1 by b1, 1 by c1. So we have 6 omega c's, 6 crossover frequencies. Then we have to check individually which is greater than it. So and accordingly we have to adjust. Let's say a1 is here, 1 by b1 is here, and 1 by c1. Like this. These are the frequencies which I have plotted. Then if there are 1, 2, 3, 4 plus 4, 8. There are 8 frequencies, 8 corner frequencies and 9 regions. See, there is no significance of the negative frequencies. So the graph will always start on the right hand side. So what happens is there are 1, 2, 3, 4, 5, 6. And yeah, this s to the power m is what? 0. S equals to 0 and s equals to 0. So 0, 0 will coincide here only. So how many regions are there? 1, 2, 3, 4, 5, 6 and next one is 7. There are 7 total regions. And at these different regions, the effect of each term will be dominating like this. So between this and this, which term will be dominating among the above term and which will be taking over of that, like this it will be there. So from 0 to 1 by a, what? And obviously m has to be greater than or equals to a for a proper transfer function. I hope you all know this proper transfer function. So m has to be greater than n. So s to the power m minus n wali term will be dominate here. Okay. Then between a and a1, so basically it will dominate here. So basically the gain plot will have no slope. It will have some constant slope and it will start some frequency. Say omega equals to 0. Substitute s equals to 0, omega equals to 0. It will start from infinite, right? From infinite it will start like this, some infinite. So means that is placed at very far distance here. It will start from here. After that, what is the effect of the terms s to the power m minus n wala term? It has to be a constant gain. So it will be like this. Then after this we have to see effect of which term is dominant. So it's between 1 by a and 1 by a1. So take this term and this term. Now you see which is greater than which and whose slope will be valid. Say a1 is greater than a, means the effect of a1 is greater than a, then the effect of the 0 will be more than the pole. So what happens? The overall will be slope will be slightly rising like this. And then similarly in the next case, a1 and b, so b is greater than a1, so again the effect of this will be rising like this. So basically the effect of pole will dominate, so it will be rising and falling at the slope of minus 20 decibel per decade. So similarly this is how you have to think and plot the gain plots. Similarly for a phase plot, angle of g of j omega, you have to see how many are this. So for s to the power m minus n terms, so it will be minus 90 into m minus n. I'll tell you what is this. Means if m minus n, okay, I'll make a table directly. M minus n, and here I'll write starting phase. If m minus n is 0, means if m equals to n, it will start from 0 degree. If m minus n is 1, it will start from minus 90 degree. If m minus n is 2, it will be starting at minus 20 degree. 3 minus 270 degree. 4 means minus 360 degree or 0 degree, and then it goes on repeating. This is the thing. This is you should take into consideration. So starting means at what point? So this is minus 90 into m minus n in degrees, and then based on this tan inverse of a by b by like this you have to do. So based on this, then you have to draw the phase plot, and then you have to shift this up and down. So by what value does it shift up and down depends on the m minus n value. So that's why the reason of, so this giving you an example of this type of transfer function is to give you a short, means a basic idea of how to draw the Bode plots, gain and phase plots, and also to prove that why phase margin is not why gain margin is not very essential, because m minus n can be 0. So the overall phase plot may not cut minus 180 degree line, so the gain margin may be undefined. So even if the gain margin is undefined, you can still design a controller and design the stability. So enough phase margin is enough to decide the stability. So that was the whole idea of this. So now we have seen gain margin, phase margin, and this. Okay, for a given plant, I think you can draw any first order or second order plot and draw the Bode plot, and then basically it's a tan inverse function. So you have to see how to bend the tan inverse function and accordingly draw the Bode plots. So now we start with the aspects of controller. As usual, means the same three aspects which we saw in the time domain. First is the stability. So for stability, the aspect is gain margin should be positive, phase margin should be positive. Means 20 log base 10 of mod of g of j omega. Gain margin is at phase crossover frequency. This has to be positive, or in absolute, this is in decibel, in absolute, mod of g of j omega pc has to be greater than 1. I'm sorry, there is a negative sign here. Yeah, because gain margin is negative. Yeah, minus 20 omega pc. Yes. So then in that case the inequality will be reversed. So I'll directly write, instead of writing this, should be less than 1. Like this. Means less than 1 means in fraction. This is in absolute. And phase margin is angle of g of j omega. Phase margin is at gain crossover frequency plus 180 degree, should be what? Greater than 0. So therefore angle of G of J omega GC should be greater than what? Minus 180 degree. These are the condition of stability in a for this controller design approach. And what is gain margin? Again we can write gain margin is what? Yeah, gain margin means whatever gain that is added by the controller. We'll write 20 log base 10, 20 log base 10 of what? Mod of D of J omega PC, the maximum value of it, that is the gain margin. Like this I'll write equals to angle of D of J omega GC, maximum of it, because margin is the maximum thing which you can add. Okay, so first is stability is done. So steady state error also we can see, but steady state error as such, we already what we decided from the this thing time domain analysis is that using a PI controller we'll get zero state error, and if you use a P controller we will not get a zero steady state error. So basically we'll always prefer a PI controller. So we'll assume that we are using PI controller. So that's why there is no need to specially analyze the second point of control design, that is steady state error. So we'll directly go to the third point or second point, that is transients, and I'll directly go to the second order plan, that is the rise time, settling time, and peak overshoot. Directly I'll go to these points. Then means how to correlate these 3 points with the our frequency domain characteristics. So I'll write time domain specification. What are the time domain specification? Rise time, settling time, peak overshoot. And what is the frequency? Frequency domain specification. They are phase margin, gain crossover frequency, or omega bandwidth of closed loop, and maybe what? Gain margin. Because and maybe gain margin and omega PC, because both are related to each other. So either you should know phase margin comma omega GC, or you should know gain margin comma omega PC, or both. And okay, I think I have made a confusion here. Okay, let's erase it. This or gain margin comma omega PC, this or this, and omega BW CL. Sorry, this also goes in OR. Okay, let's. Bandwidth is not needed. Bandwidth is for closed loop. So this frequency domain analysis is only for open loop, means loop transformation analysis. So these are the time domain and frequency domain specifications, and we will know how to correlate them. So I'll write correlation between time domain and frequency domain parameters. Specifications. We'll see how to correlate each other. The value of Kp Ki will be same in both the cases, but then given the controller is designed using different design approaches, what is the correlation between their respective specification or respective parameters? Okay, so what we see is that rise time, settling time are a function of phase margin. But what is the function, how they vary, that we'll see. Now, also zeta damping factor, you can write zeta for a second order plant. That depends. Okay. So let's take an example of a second order plant. Now the second order plant example which we took in the last class, that is omega n square pi s square plus 2 zeta omega n plus omega n square, that is the closed loop response of that plant using unity feedback and without any controller. So I'll write g of s will be omega n square divided by s into s plus sigma, where sigma is zeta omega n. This is the normal transfer function of a second order plant. Now GCL of S is omega n square by s plus sigma whole square plus omega d square, where omega d is omega n under root of 1 minus zeta square. This is the thing. GCL of this means this is G of S without controller. GCL, this is the GCL of S and this is G of S. So the second order plant should be this when I say a second order plant. So then we'll see what are the crossover frequencies and then margins. So first we'll find omega gain crossover frequency. For omega gain crossover frequency, what is the thing? Mod of G of j omega. Okay, first let's calculate the margins. So first let's convert the transfer function in the realizable form. G of j omega equals to omega n square plus by j omega into j omega plus sigma. So into j omega minus sigma into j omega minus sigma. So if we just solve it, it becomes first we'll write the real part. First is this multiplication, j square is minus 1, so minus omega square omega n square omega n whole square, and the other part is minus omega n square into omega sigma j. Yeah, j omega minus sigma j omega minus sigma j omega into omega n square. Yeah, divided by j square will be minus 1, so minus omega square into a plus b into a minus b. It will be a square minus b square, sigma square plus omega square. So what happens? The minus will get cancelled, so it will be omega n square plus sigma omega n square j divided by omega square into sigma square plus omega square. So it will be what? Omega n square divided by sigma square plus omega square plus sigma omega n square by omega into sigma square plus omega square into g of j omega, and the angle will be tan inverse of So this will get cancelled, this will get cancelled, so it will be tan inverse of sigma by omega. And from this, what is mod of g of j omega? It will be under root of omega into the power 4 omega to the power 4 plus sigma square omega into the power 4 divided by omega square into sigma square plus omega square. So it will be omega n square by omega square under root of and omega square omega to n to the power 4 and omega square will take out into omega like this. So it will be 1 plus sigma square, so not 1 omega square omega into the 4 into omega square we are taking outside, so omega square plus sigma square divided by sigma square plus omega square. So this will get cancelled and this will be under root of this. So numerator will be omega n square by omega into under root of sigma square plus omega square. This is mod of g of j omega, this one, and this is angle of g of j omega. So this is the thing. Now I'll not draw the graph, I'll just derive the crossover frequencies and gain margins and all like this. So first is the omega gc. I'll write in absolute scale. At omega gc, what is the frequency at which the gain is 1? So 1 equals to mod. So omega n square divided by omega into under root of sigma square plus omega square. Given that whatever I have derived is correct, then I'm just drawing it. So omega, we have to solve for omega and then we'll find what is the omega gc. Omega square into sigma square plus omega square equals to omega into the power 4 omega to the power 4 plus sigma square omega square minus. So then we can find and then we can find omega using this expression, and omega we'll write omega as omega gc, and we'll take only the positive value because there is no significance of negative value. So this is the omega gc, correct? So we'll neglect the negative sign. So omega gc is what is sigma? Zeta into omega n. Zeta into omega n. Minus zeta square omega n square plus zeta to the power 4 omega into the power 4 plus 4 omega into the power 4 divided by 2. Like this, something we have derived here also plus minus, so we'll take only the positive sign. And omega should only be positive and it should not be complex, only positive and real. So inside we should take positive sign, and outside also we should take positive sign plus sign, and then we should solve. So omega n square will take common, then omega n will come here, omega gc zeta plus under root of zeta to the power 4, here omega to the power 4 plus 1, right, divided by 2. I think this is the expression. So this is the relation between gain crossover frequency and the zeta. So it is a function of zeta. Omega gc is a function of zeta. Similarly, we can find the omega pc. Omega pc is where the angle is what? Minus 180 degree. So minus 180 degree equals to tan inverse of what? Sigma by omega. Sigma by omega. Omega is omega pc. So tan of minus 180 degree equals to sigma by omega pc. Tan is a sine of 180 degree, sin pi is 0. Actually, at 180 degree it means that it cuts at multiple points. So sin 180 degrees, I think tan 180 degree is 0. So omega pc will be 0. So in this omega pc we won't get a relation. In gain crossover frequency only we got a relation. So this is another reason why phase crossover frequency or gain margin may be optional, but gain crossover frequency and phase margin are needed for control the design. So third is the phase margin. Phase margin is angle at this plus 180 degree. Phase margin means tan inverse of sigma by omega gc plus 180 degree. This is the gain margin, and phase margin, and the gain margin is minus 20 log base 10 of mod of this at what is mod? Omega n square. Omega n square divided by, for gain margin we should take the phase crossover frequency, so omega pc into under root of sigma square plus omega pc whole square. Like this we can find the gain margin. Now here again, if omega pc is 0, this is 0, so under root of 0 denominator becomes infinite, so gain margin becomes undefined. This is also classical example of what? For the just like the first order system. So we'll take the phase crossover frequency and the phase margin and gain crossover frequency, not phase crossover frequency. The gain crossover frequency and phase margin to be under considerations. Actually, there is some problem here. It should be minus 90 degree minus of this. Why? Because g of s you can write as omega n square by s into 1 by s plus, I think it is 2s plus 2 s plus sigma. So angle of this is minus 90 degree and angle of this is tan inverse of sigma by omega minus sigma by omega. So just add this. So there is some mistake, minus 90 degree. Minus 90 degree. So it becomes like this. So it becomes minus 90 degree or plus 90 degree equals to tan inverse of sigma by omega pc. So tan 90 equals to sigma by omega pc. So sin 90 by cos 90. So this becomes infinite. So omega pc almost tends to 0, like this. Similarly here, if you put here infinite, it will always tends to 0. Here it will be 0. So again, phase gain margin and phase crossover frequency are optional to take. You can take gain and gain margin and gain crossover frequency and phase margin. So here also the gain margin becomes 180 degree plus this, so minus 90 degree and minus this, so it becomes, I'll just shift it down, it becomes 90 degrees minus tan inverse of sigma. Sigma is zeta omega n by omega gc. This becomes the phase margin in degrees. This is the phase margin and this is the gain margin. So we have correlated phase margin and gain margin as a function of zeta. Okay, but this overshoot is exponential of minus pi zeta by under root of 1 minus zeta square. So if you substitute here, they'll also become a function of overshoot, because overshoot is a time domain specification. Overshoot here, zeta is optional, so we have related the gain margin, phase margin with the overshoot, and similarly we can rate with the rise time and settling time. So for rise time and settling time we should do the closed loop response. Here we are doing only the loop transfer function or only of the plant. Now we know for stability we know the phase margin and gain margin has to be positive, but what should be the maximum value of phase margin? The maximum value of phase margin depends on the plant. So PM minimum equals to 0 and PM max, it depends on the plant, on the plant transfer function. It depends on the plant. So it can be in the range of 0 to 90 degree, 0 to 45 degree, or 0 to 180 degree. So let's say if the plant transfer function is only a gain, simple gain, in that case the phase will always be what? 0 degree. So the phase margin will be what? Minus 180 degree. 0 minus of minus 180, it will be plus 180 degree. So means you can add 0 to 180 degree phase using the controller. So it depends on the plant. So PM max, let's say it's a gain, so it will be 180 degree plus 180 degree. So you can write 0 is less than phase margin is less than 180 degree. Maximum possible phase margin is 180 degree. That is when the transfer function of plant is a constant gain, unique gain only. So phase margin and zeta relation we have already seen like this. It is of some tan inverse of this thing. So if we just set a range of phase margin, if you want to plot phase margin versus zeta versus MP. So phase margin will be on x-axis, this will be on y1 axis, and this will be on y2 axis. If we just plot between this range, so say this is y1, this is x, and this is y2, this is MP, this is zeta, and this is phase margin. So let's say this is 0 degree and this is 180 degree, so this will become 90 degree. Typically we select it in the range of 0 to 90 degree or 0 to 60 degree basically for power electronic converter. So this is 45 degree and this is 60 degree. Typically for power electronic application, this is preferred range of phase margin. Preferred range. So phase margin versus zeta. So phase margin, you can write phase margin as almost directly proportional to zeta and phase margin almost inversely related to peak overshoot using this formula MP. First, phase margin versus zeta formula is this. Substitute zeta with MP using this equation 2 and 1. Solving 1 and 2, you can get relation between phase margin and MP and just approximate that in some small range of angle. Then you will observe that this is the, okay, let me change the color. let me do this color. This is 0 degree. This is what? MP. So what? MP versus phase margin is false. It falls like this. It falls, and this is for zeta. For zeta, it rises like this. So this is almost constant, almost a linear in this range. So basically zeta, you can almost write phase margin by 100, phase margin degrees by 100 using this identity. For 45 degree less than phase margin in degree less than 60 degrees. Basically this range is preferred for control of power electronic converters. This is just an approximation of this thing. So this is how we correlated the time domain specification with the frequency domain specification. For rise time and settling time, you have to do GCL of S to correlate TR TS with what? Phase margin, gain margin. We need to solve this. So basically G equivalent of S is what? Omega n d of S into G of S divided by 1 plus d of S into G of S, where G of S is omega n square by S into S plus sigma. This we have to put, and d of S is say Kp. So Kp plus Ki by S, SKP. So Kp S plus Ki by Kp. Like this, we'll write. Sorry, Kp by S. SKP plus Ki. So Kp out, Ski by Kp. Yeah, this is the control. And then after first d of S is this, d of S is this. Then what you have to do to find control, to tune the controller and on Ki Kp, you should know. Then for this G current of S, you have to plot the response in time domain. Measure its rise time and settling time, and then substitute, means basically then you can find its correlation with the Kp Ki parameters. So ultimately what happens is Kp Ki are a function of phase margin, gain crossover frequency, and which are a function of what? Rise time, settling time, peak overshoot. This is for frequency domain. This is for time domain. So how to get Kp Ki as a function, as a G of TR, TS, MP, which we already saw in the last lectures for controller of design in time domain. Now how to find Ki Kp as a function of f of phase margin, omega GC. This we are doing right now in frequency domain. And how f of x are related to G of x is which is what we saw just now. We correlated phase margin, gain crossover frequency with MP, overshoot. We can correlate that with TR and TS also, but for that we have to do some additional computation. But that will not help us. We want to tune Kp Ki based on either F or G. So basically it is a tedious task to correlate phase margin and omega GC with TR and TS. But I have just given you an idea of how to correlate PM and omega GC with MP, peak overshoot. Correlation you can do anytime. You can do the correlation just to verify that your solution is same for both the time domain and frequency domain. That is, for the same Ki Kp, you are getting the desired rise time, settling time, peak overshoot, as well as your expected phase margin and omega GC. So these parameters, just like time domain, the parameters phase margin, omega GC are known to us, or we have to select. You have to select it and then you have to tune Kp and Ki. This is the approach in the frequency domain. And for frequency domain, we consider OLTF. That is D of S into G of S is considered in frequency domain. So in that case, what so for controller design, we take the open loop transfer function, because we know whatever is the gain margin and phase margin, or whatever is the gain or phase to be added in a closed loop response to be stable, that is to be added by the controller. So that's why we have to take open loop transfer function for tuning the controller parameters. So now the last topic of this lecture is generic approach for PI tuning in frequency domain. Okay, so as I told you, as I just gave you example of a first order plant and I have drawn the Bode plots and all. So in that case, omega GC, now this is for a plant, right? This mod of G of J omega GC at J omega dB and angle of G at J omega. So basically these are for the plant. So basically omega GC is a function of plant, is the nature of plant. Now you can't change the nature of the plant. You know what is a plant. The plant is already modeled in Laplace domain. That is the transfer function. Means for a given part omega GC is known. Or basically you have to assume omega GC. Again crossover frequency. Okay, that depends on the application, like for a switching application and all. So step 1 in any approach, generic approach, is assume omega GC, which means basically assume omega GC, then draw the Bode plot, tune your KPK, then draw your Bode plot of the open loop transfer function, and then say that, and then see that gain crossover frequency and this gain crossover frequency are matching with each other with the expected phase margin. Step 1 is to assume omega GC. Step 2 is the what is the step 2? Step 2 is the for phase margin. Phase margin is the maximum gain. So assume, but there are some rules to assume omega GC, and there are similarly some rules to assume what? Angle of T of J omega at, this is related to phase margin, so this is at gain crossover frequency. Assume this. So you know that maximum G of J of omega GC max value is phase margin, which is depends on plant. Okay, so you can't assume the angle of T of J omega GC more than the phase margin. Maximum value of this is this. Okay, and what is the minimum value? 0, because phase margin should be positive. So I can write 0 less than angle of D of J omega GC less than PM. So using this, assume a angle of D of J omega GC. Step 1 is assumption of omega GC. For omega GC, basically what we do for power electronic converter, omega GC is omega switching by 10 or omega switching by 100 or omega switching by 200, omega switching by 1000. This all we can assume. That depends on the plant. So in the next lecture we'll take an classic example of a dual loop or single loop control of any DC-DC converter, and then I'll tell you how to assume omega GC. So this approach, generic approach of tuning PI controller, is based on the assumption of that you know what is omega GC and you know what is angle of D at J omega GC. Then comes the step 3, tuning Kp and Ki, or basically finding Kp and Ki. So each set of these two values, omega gc and angle of d at j omega gc, will have a unique set of Kp and Ki. If you change them, they'll also change. But Kp Ki usually are a single value, so we have to just get only single value of Kp and single value of Ki at a given omega gc and angle of d at j omega gc. So now I'll write is, then comes the crucial step 3. As I said, for tuning PI parameters in a frequency domain analysis, you take OLTF, that is this into this. So I'll write G open loop of S, that is D of S into G of S. What is D of S? Kp by S into S plus Ki by Kp, correct, into G of S, generic plant. I'll say generic plant. Okay, generic plant. I hope it's correct. Where is that? Yeah, Kp plus Ki. So Skp plus Ki by S. So Kp by S and Kp by S into S plus Ki by Kp. Yes, this is correct. So this is the thing. Now I told you phase margin is what? The angle that can be at phase margin for a plant, means so I said earlier that phase margin is what? Angle of G at j omega. Phase margin is at gain crossover frequency plus 180 degree. Okay, this is the margin, but who will add this angle? This is given by the plant, sorry, controller, given by angle of D at J at the same frequency it should give, right? Omega gc. So this. So what I mean to say is, this maximum value of this is this. Maximum of angle of D of J omega gc, correct, is this angle of G of J omega gc plus 180 degree. Okay, so let's say we assume some this value. So maximum value of this is this. So similarly, for what is the phase margin for OLTF? The phase margin for OLTF is angle of G at j omega gc plus angle of D at j omega gc plus 180 degree. Same logic, just replace this is D of S into G of S. Okay, so this is the assumed phase margin of the OLTF. Just replace the plant with OLTF plant, D of S into G of S, and for OLTF angle just gets added, right? Angle will just add the angles. Okay, so what is the phase margin of OLTF? Okay, or you can write angle of G OLTF at j omega gc plus 180 degree. Now what is this PM at OLTF? This is the one which you are assuming. So this is the one which you are assuming. You are assuming this angle. Assuming the angle which is given by the controller is nothing but the phase margin of OLTF. So you are assuming this. Step 2, you are assuming phase margin at OLTF like this. So this is phase margin at OLTF. I'll just write PM at OLTF equals to PM star, which is assumed, which is less than what? Angle which is less than angle of G at j omega gc plus 180 degree. This is the maximum value of PM star. Okay, so from this equation what you can write? Angle of G OLTF at j omega gc is PM star minus 180 degree. This is equation number 1. Similarly, what we can write? Gain in absolute will write mod of GOLTF at j omega gc is what? Just multiply the gain. Mod of D of j omega gc into mod of G of j omega gc. Correct. So D of j omega you can write what was it? Kp by s. Okay, s kp plus ki by s. So j omega kp plus ki by j omega into j omega into j omega. So it will be minus omega square. J square is minus 1 minus omega square kp plus j omega ki. So omega, this square and this square will get cancelled. It will be minus omega kp plus ki into j by omega, or it will be omega kp plus ki j by omega, or simply kp, sorry, this will be minus kp minus ki by omega into j. This will be d of j omega. Therefore d of j omega gc will be kp minus ki by omega gc into j. Correct. This will be like this. This is equation, say this is 1, this is 2, and this is 3. Similarly, yeah, I think equation in equation 2 will remove the mod. I think it still makes sense. Yeah, we'll just write G of OLTF is D into G. Then what is G j omega gc? This we will write in the complex domain, means R at an angle theta. What is R? So just like what we did for the plant, we'll do for the open loop transfer function. That is, what is the gain in absolute value when the frequency is at omega gc? I think gain crossover means the frequency at which the Bode plot crosses the 0 in decibel or 1 in absolute. So it is 1. Correct, it is 1. And what is the angle? What is the angle of G of OLTF? The angle of G of OLTF is using equation number 1. That is PM in star minus 180. This is whole in degrees. So this is the equation number 4. Then what is 3, 4. So yeah, and for a generic band, G of j omega gc is what? Mod of G at j omega gc and angle of G at j omega gc. Very generic term. So then using 2, 3, 4 and 5, or using 2, 3 and 5 in equation 2, what we'll get this. So I can write d of j omega. Now you'll understand why I've written here in polar coordinates and here in rectangular coordinates. D of j omega gc using equation 2. D of j omega gc is what? G OLTF. G of OLTF at j omega gc divided by g at j omega gc. This is equation number 6. So I'll write using 2. This is equation 6. Then putting what? 3, 4 and 5 in 6. You can get the kpk value easily. I'll tell you how. Now here it is in denominator. r1 e to the power theta 1 divided by r2 at an angle of theta 2 will be what? r1 by r2 at an angle of theta 1 minus theta 2, right? We'll use the same principle here. So therefore, what is d of j omega gc? It is equation number 3. So kp minus ki by omega. But what is omega? Omega is omega gc into j. This is in rectangular coordinate. Let it be as it is. We have converted only the numerator by denominator in the polar coordinate. What is g OLTF? 1 at an angle of PM star minus 180 degrees divided by what is g? Mod of g of j omega gc at an angle of g of j omega gc. Correct. Then what will be the RHS? 1 by mod of g of j omega gc in at an angle of what? PM star minus 180 minus what? Angle of g at j omega gc. This will be the angle. Okay, so using the identity r cos theta plus j sin theta is r at an angle of theta. Okay, so thus therefore what is the RHS? Yes, r at an angle theta. We'll just convert it to rectangular coordinate in the RHS. So it will be r cos theta plus j r sin theta. So it will be r is this 1 by mod of g of j omega gc into cos theta into cos of theta. Okay, so I write some theta. Okay, plus j sin theta, where theta is PM star minus 180 minus angle of g at j omega gc. Okay, then equating LHS to RHS, what we'll get? Kp, right? What is Kp? Kp is cos theta by mod of g at j omega gc, and what? Minus ki by omega gc. So minus ki will be omega gc into r sin theta. So ki will be minus omega gc into sin theta by mod of g at j omega gc. You got it? Final expression I'll write kp equals to cos of this angle is PM star minus 180 minus angle of g at j omega gc. Now cos of minus theta is cos theta. So what I'll write? I'll do reverse all the signs and I'll write like this. minus PM star, and I'll erase this, I'll shift this there. Yeah, divided by what? Mod of G at J omega Gc, and Ki is minus omega Gc. So minus sign is already multiplied there, so it will be omega Gc sine of same angle 180 degree. This is in degrees. 180 degree plus angle of G at J omega Gc minus PM star in degrees divided by mod of G at J omega Gc. This is how you tune Kp and Ki for a generic plant. Okay, so in this lecture we started with basics of frequency domain analysis. So yeah, in frequency domain OLTF, then we saw the specification of frequency domain, margins and crossover frequencies. Then we took an example of a first order plant, that is a basic low pass filter. We drawn the Bode plots, we saw what is the gain margin, phase margin and the crossover frequencies of it. Then a generic example in Bode plot I have shown how to denote in a graph Bode plot, how to denote like this phase margin and gain margin. Then their mathematical expression, generic mathematical expression for a plant for the crossover frequencies and margins. Then I have also told you like how to for a nth order generalized plant, how to draw the Bode plots, how to find the corner frequencies and how to change the gain accordingly, and how to shift the phase plots up and down using this, and why gain margin and phase crossover frequency are not much considerable for stability analysis, and only phase margin and gain crossover frequency are needed. That also I have explained in this example. Then the contour aspects, just like stability and transient requirement. I have correlated the time domain specification, which is only the peak overshoot, with respect to the frequency domain specification by correlating them as a function of each other, and then some conclusion is drawn, like in a small range of phase margin, the phase margin versus zeta relation is almost linear, and phase margin versus peak overshoot relation is almost inversely proportional. So when you say if you increase the damping, phase margin will increase, or with increase of phase margin, damping will increase but peak overshoot will decrease. Okay, similarly its effect on rise time and settling time you can see by doing the closed loop analysis. So if the contour is fast, means the frequency is high, the gain crossover frequency or the bandwidth is high. Bandwidth is the frequency at which the closed loop Bode plot gain magnitude is 1 by root 2 in absolute, or minus 3 dB in decibel scale. So then a generic approach to tune the PI parameter for any generic plant, order plant, we have discussed step 1, step 2 by assuming a gain crossover frequency and assuming maximum phase which a controller can put, or the phase margin of, so the angle which is put by the controller, which is limited by the phase margin of the plant, is nothing but the phase margin of the open loop transfer function. Correct. So assuming in step 2, assuming angle of D at J omega G is nothing but assuming PM star. PM star is PM at OLTF. Doing this, we did it. So basically whatever is the definition of the phase margin and gain margin will be the same for a plant and for a open loop transfer function, that is G into D, and same is valid for G as well. Then based on this, using polar and rectangular coordinate transformation, we have found the Kp and Ki values for a given gain crossover frequency and phase margin. Phase margin you have to assume, and gain crossover frequency you have to assume. This is the Ki Kp parameter. And once knowing this Ki Kp, if you draw the Bode plot of the open loop transfer function, you will get exactly the Bode plot with the gain crossover frequency happening exactly at omega Gc, and you will get the same phase margin as what you have assumed here for the OLTF. So this is how to verify that your Kp Ki are correct or not for a given omega Gc and Pi. So using this Ki Kp, substitute substitute it in d of s. Substitute this kp and ki using this formula in d of s. Then give a command in MATLAB that bode of d of s into g of s, and then see the gain, or you can do margin. There is a command margin of d of s into g of s. See the gain and the phase plots. In that plots you will see that whatever is the gain crossover frequency, whatever is the phase margin, that exactly matches with the one which you have assumed, which means that the solution is correct. And then here we get omega gc and pm, and then we verify like this. So if we change, if the plan changes, assumption also slightly changes, but you know what is the range in which you should put the pm max, or pm star should be greater than 0, less than what? Angle of g at j omega gc. So basically it all depends on how you assume the omega gc, gain crossover frequency. So unless and until switching frequency changes, the gain crossover frequency will not change. It is all assumed to be almost constant. So that's it. In the next lecture we'll see the example of PI tuning using actual DC-DC converter, using like single loop control, current control, or dual loop control, inner current control, outer voltage control, and we'll discuss it further.